Welcome back, everyone. Ready for another deep dive. Today we're, circling back to some geometry basics. But trust me, with this 10 circles.pdf source, it's way more exciting than just dusting off your old textbook.
Absolutely. Circles, they're everywhere. But most of us don't realize the hidden depths they have, the way they shape everything from, the buildings around us to the music we hear.
That's what I love about these deep dives. You never know what you'll uncover. So our source kicks off with the definition of a circle, the whole set of points equidistant from a center thing.
And that distance, that's the radius. The circle's like ID card. It tells us the size, the shape, everything.
Right. It's the key ingredient. Speaking of which, I noticed they mentioned all these everyday objects, reels, bangles, those old school clock faces, even coins. It really hits you how common circles are.
We take them for granted, but each one, like a wheel, it works because of the circle's properties. That constant distance from the center allows for smooth rolling. Imagine a square wheel. Chaos.
Mind blown. It's like circles are the unsung heroes of, not falling over when we try to move.
Exactly. And that's just one example. But before we go too far, maybe we should, get our terms straight. Chords, diameters, all that jazz.
Yeah.
Like a crash course in circle lingo.
Love it. So first up, chords. Basically any line that connects 2 points on the circle. Yeah. Like a bridge across the circle's edge.
Spot on. And then there's the VIP chord, the diameter. This one goes all the way across, passing right through the center, like slicing a pie perfectly in half.
Ah, the diameter. And that's why it's the longest chord possible, right?
Yeah.
Because it's like 2 radii stuck together.
Exactly. It's got the inside track. And speaking of curves, what about arcs? They're like the curved segments of the circle's edge.
Right, like the crust of a pizza slice. So if the arc is the crust, then the segment would be the whole slice, right? And then, of course, we've got the total length of the circle's edge, like if you were measuring it with a tape measure.
You've got it. And all these terms, they're connected in really cool ways, which I think we'll start to unpack now.
Okay, this is where it gets really interesting for me. The source mentions this connection between angles and chords. It's like some kind of secret geometric language. Tell me more about this angle magic.
All right, picture this. You draw a chord across the circle. Now, draw 2 lines from the ends of that chord to the center of the circle. See the angle they make. That angle is, we say, subtended by that chord.
Okay, I'm visualizing it. So the chord's like the base of the angle and the center of the circle is like the pointy part.
You're getting it? Now get this. If you've got 2 chords that are equal, guess what? They always make equal angles at the center too.
So if the chords are like twins, their angles are twins too. It seems like something you'd only care about in, math class, not real life.
You'd be surprised. Think about bridges or any structure that needs to be stable. This equal chord, equal angle thing. That's what helps distribute weight evenly so nothing collapses. Pretty important.
Wow, I never thought of it like that. Circles really are the hidden support system we never knew we needed.
Okay, so we've got equal chords making equal angles at the center. What other angle action does our source have in store for us? I'm hooked. Well, there's this other amazing relationship between the angle at the center and the angle that same chord makes, but at a point on the circumference of the circle, not the center.
Hold on, let me get this straight. We're talking about 2 different angles, right? Both made by the same chord, but one's at the center and the other's out there on the edge.
Exactly. And there's a special connection between them, a kind of mathematical rule.
Does it have to do with the angle at the center being twice the size of the other one? I think I saw that in the source.
Sharp eyes. That's Theorem 10.8 in action. Official circle geometry stuff. And it's a game changer.
Theorem 10.8 sounds serious. So it's basically saying no matter where I pick a point on that circle's edge, the angle the chord makes from there is always half the size of the angle back at the center.
You got it. And this, my friend, unlocks all sorts of ways to solve tricky geometry problems. It's like a shortcut key.
Okay, my brain's officially doing loop-de-loops with all these angles and chords. Circles are way cooler than I ever gave them credit for.
We're just getting started.
Okay, give me a sec to process all this angle stuff. It's wild how much complexity there is in a shape that seems, so basic.
That's the thing about circles, right? They're like deceptively simple, but then you dig in and there's this whole world of possibilities.
A world of possibilities, I like that. Speaking of which, I noticed the source mentioned something about perpendicular lines, chords, all that. What's the deal there?
Perpendiculars. Classic circle geometry stuff. So picture a chord drawn across your circle. Now imagine a line straight down from the circle center, right through that chord, but at a perfect 90-degree angle. perpendicular.
Okay, got it. Like that line from the center is cutting the chord right in half, making a perfect T shape.
You got it. And not just any half. This perpendicular line, it always bisects the chord, meaning it splits it into two perfectly equal segments.
No way. It's like circles have some kind of built-in level, making sure everything's perfectly balanced. Is there like a theorem for this too? There's gotta be.
Of course. We got to keep things official. It's a theorem 10.3, coming in clutch. And just like those angle theorems, this might seem kind of, I don't know, abstract. But think about it. Bridges, buildings, anything that needs to stand up straight and not fall over, this theorem's working behind the scenes.
Circles, secretly holding our world together. Okay, so we've got all these lines and points and circles. It makes you wonder, how many points do you actually need to define a unique circle?
That's a great question, like a little geometry puzzle. Let me ask you this. How many points to define a straight line?
2, right. So I'm guessing a circle needs at least 3.
You're on a roll. But there's a catch. All 3 can't be on the same line. They got to be what we call non-collinear, all spread out.
Non-collinear, fancy word, but why does that matter?
Because if they were all in a line, you could draw like a million circles that all go through those points.
Right. It'd be like, I don't know, trying to draw a circle around a ruler. You could draw forever. But with 3 points, not in a line, there's only one circle that fits perfectly.
Exactly. Theorem 10.5 lays down the law. 3 points, the magic number for a unique circle.
Okay, I'm seeing a theme here. 3 points, chords making angles, it's all connected.
You're getting it. Circles are all about patterns and connections. Speaking of which, ever thought about what happens when a circle meets a four-sided shape?
Like a circle and a quadrilateral. Sounds kind of like a weird geometry party, but okay, I'm game.
Is that where cyclic quadrilaterals come in? I think I saw that term.
Bingo. It's a mouthful, but basically a cyclic quadrilateral is just a four-sided shape where all 4 corners, we call them vertices, are touching the circle, like the circle's giving it a big hug.
I can see it. But what makes these cyclic quadrilaterals so special? They just seem like, I don't know, regular quadrilaterals to me.
Well, hold on to your hat, because here's the kicker. In any cyclic quadrilateral, if you add up the opposite angles, guess what? Always equals 180 degrees, no exceptions. Seriously. No matter how wonky or weird the cyclic quadrilateral is, those opposite angles always add up to 180.
You got it. And that little fact, Theorem 10.180, opens up a whole treasure chest of problem-solving tricks.
It's like circles have all these hidden rules just waiting for us to discover them. I'm telling you, circles are way cooler than I ever realized.
Told ya, they're full of surprises.
Okay, we've got chords, angles, perpendicular bisectors, even quadrilaterals hanging out with circles.
Circles really do bring it all together, don't they? It's all about the connections, the patterns. And there's one more connection I think you'll find pretty neat. Remember how we talked about a chord basically dividing a circle into 2 arcs?
Yeah, like a pizza cutter, right. Except our slices are arcs, not pepperoni and cheese.
Exactly.
Yeah.
And just like pizza slices, arcs can be different sizes. We call the smaller one the minor arc and the bigger one the major arc. Pretty straightforward.
Okay, makes sense, but what's so special about them? They're just, well, arcs, right?
Well, turns out those equal chords we talked about, they don't just create equal angles at the center, they also create congruent arcs.
Congruent. Wait, so not just equal in length, but like exactly the same shape too.
You got it. It's like those matching games, find the 2 identical pictures. If you could pick up one arc and plop it right on top of the other, they match perfectly.
No way. That's so cool.
Yeah.
Circles are full of surprises. What else can you tell me about these congruent arcs? Anything else they do?
Well, remember how we said a chord makes an angle at the center of the circle? We can also say that the arc cut off by that chord, usually the minor arc, subtends that same angle at the center. It's like their thing.
Okay, hold on. So the chord's like the base of a triangle, center of the circle is the top point, and the arc is like the curved bottom of that triangle.
You're a natural at this. Now, here's the real kicker. Remember that angle relationship we talked about? How the angle at the center is always double the size of the angle the same chord makes at the edge of the circle?
Yeah, Theorem 10.8. Right, the
Yeah.
parent angle and its little sibling. I won't forget that one.
Good, because it pops up again. That same relationship applies to these arcs and angles too.
Yeah.
The central angle's measure is always twice the measure of the inscribed angle that, intercepts the same arc.
Let me see if I've got this straight. If I draw an angle using the ends of an arc, and the center of the circle is the point, that's the central angle. Right. Then I pick any random spot on the rest of the circle's edge, draw an angle using those same arc endpoints. That's my inscribed angle. And no matter what, that central angle is going to be twice as big as the inscribed one.
Exactly. It's like the central angle is the boss, always calling the shots.
That's wild. It's like circles have this whole secret geometry code, and we're just figuring it out.
That's what makes it fun, right? It's
Yeah.
all about making those connections. And here's one more to really make your head spin. What happens when that arc we were talking about is a semicircle?
A semicircle, you mean like when the chord cuts the circle perfectly in half, making an arc that's half the circle's circumference?
You got it. Now think back to those inscribed angles we were talking about.
The ones where you can pick any point on the circle's edge.
Right. So when that arc is a semicircle, guess what? No matter where you put that point on the opposite side of the circle, the angle made by that point and the ends of the semicircle, it's always a right angle, a perfect 90 degrees every time.
No way. That's incredible. So any angle inscribed in a semicircle has to be a right angle.
Has to be. It's
Yeah.
one of the coolest and most useful theorems in the book. Really comes in handy.
This whole deep dive has been amazing. I mean, we went from basic circle stuff to like mind-blowing theorems. Who knew there was so much to learn about a shape that seems so simple?
That's the beauty of it, right? Circles, they're full of surprises.
I'm definitely seeing them in a whole new light now. I'll never look at a pizza the same way again.
I told you, circles are everywhere.
Well, on that note, we've come full circle. Thanks for joining us, everyone. Keep exploring those circles. You never know what you might find.